Imagine a world where scientists believed in an invisible substance. They thought this substance permeated the entire universe. This substance, they called the luminiferous ether, was thought to be the medium through which light waves traveled. Much like sound waves need air or water to propagate, 19th century physicists believed light needed the ether. The ether was a perplexing concept, simultaneously ethereal and omnipresent. It was thought to be at absolute rest, providing a fixed reference frame against which the motion of celestial bodies could be measured. The ether was a cornerstone of classical physics, seemingly indispensable for understanding the nature of light and the cosmos. The ether theory was not without its critics. Some scientists questioned its necessity and the lack of direct evidence for its existence. However, the prevailing scientific consensus held that the ether was real. It was a testament to the power of established paradigms and the human tendency to cling to comfortable explanations, even in the face of mounting uncertainty. The stage was set for a scientific showdown, a clash between established theory and experimental observation that would redefine our understanding of the universe. In the mid-19th century, James Clerk Maxwell formulated his elegant equations, describing electricity and magnetism. Maxwell's equations were a triumph of theoretical physics, unifying these two seemingly disparate forces into a single electromagnetic force. However, Maxwell's equations presented a conundrum for the ether theory. His equations predicted that electromagnetic waves, including light, traveled at a constant speed. This speed, now known as the speed of light, was calculated to be approximately 299,792,458 meters per second. This presented a problem because it violated the principle of relativity as understood at the time. According to classical physics, the speed of an object is relative to the observer. If you throw a ball forward on a moving train, the ball's speed relative to the ground is the sum of the train's speed and the speed at which you threw it. However, Maxwell's equations implied that the speed of light was absolute, independent of the observer's motion. This was a profound implication that challenged the very foundations of classical physics. To reconcile Maxwell's equations with the ether theory, scientists proposed that the Earth and other celestial bodies moved through the stationary ether. This motion, they reasoned, should create an ether wind. Just as air resistance is greater when riding a bicycle into a headwind, the speed of light should be affected by the ether wind. If the Earth is moving through the stationary ether, then the speed of light should be different depending on whether it is measured in the direction of the Earth's motion or perpendicular to it. Detecting this difference in the speed of light became the holy grail for physicists seeking to prove the existence of the ether. The challenge was to devise an experiment sensitive enough to measure this minute difference. In 1887, Albert Michelson and Edward Morley set out to detect the elusive ether wind. They designed an ingenious experiment using an instrument called an interferometer, invented by Michelson. The Michelson interferometer was a marvel of precision engineering. It used a beam splitter to divide a beam of light into two perpendicular beams. These beams were then reflected by mirrors and recombined, creating an interference pattern. The interference pattern is sensitive to any difference in the path length traveled by the two beams. Michelson and Morley reasoned that if the ether existed, the beam traveling parallel to the Earth's motion through the ether would take a slightly different time to travel the same distance as the beam traveling perpendicular to the ether wind. This difference in travel time, however small, would manifest as a shift in the interference pattern. The expected shift in the interference pattern was extremely small, but Michelson and Morley were confident that their instrument was sensitive enough to detect it. They conducted their experiment in a basement laboratory at Case Western Reserve University in Cleveland, Ohio. The results of the Michelson-Morley experiment were startling. Despite their best efforts, Michelson and Morley could not detect any difference in the speed of light, regardless of the direction of the interferometer. They repeated their experiment at different times of the year, when the Earth's motion through the ether should be different, but the result remained the same. The ether wind, if it existed, was nowhere to be found. The null result of the Michelson-Morley experiment sent shockwaves through the scientific community. It was one of the most important failed experiments in history, as it challenged a fundamental assumption of classical physics. The experiment cast serious doubt on the existence of the luminiferous ether. It seemed that light did not need a medium to propagate, contradicting centuries of scientific thought. The Michelson-Morley experiment created a crisis in physics. Scientists struggled to reconcile the null result with existing theories. Some proposed modifications to the ether theory, suggesting that the Earth might be dragging the ether along with it. However, these ad hoc explanations were ultimately unsatisfactory. The crisis in physics persisted for nearly 2 decades until Albert Einstein, a young patent clerk working in Bern, Switzerland, proposed his groundbreaking theory of special relativity in 1905. Einstein's theory dispensed with the need for the ether altogether. He postulated that the speed of light in a vacuum is the same for all observers, regardless of their relative motion. This audacious idea revolutionized our understanding of space, time, and gravity.